चालू करती हूँ. So today we will see Newton's laws of motion. In this, we will first see the three laws of motion. Okay, so the first law tells us that if a body is at rest, it wants to be at rest. If it is in motion, it will continue to do so until an external force is applied to it. It also indicates us inertia. So, if a body is at rest, it will continue to be at rest, and if a body is moving, it will continue moving unless and until there is an external force acting on it. So, when in this, if the external force is zero, then the acceleration will also be zero. Now, the second law of motion. This tells us that if a net external force is applied, then it must be the rate of the change of momentum, and in this momentum, it is the parameter to measure the motion. So, if the force is here, the external force is not zero, then it will give us F is equals to ma. And in this, momentum will be P is equals to mv. Here, it also indicates impulse. Impulse is the change in momentum or a very large force exerted in very small time. Okay, so now we will see Newton's third law of motion. Okay, this tells us that every action has equal and opposite reaction, and because of this force, reaction force, motion is caused only because of this reaction force. Okay, so here the force always acts in pair. This is the main point. It always acts in pair at same instant and also on different bodies. Okay, so now we will see the free body diagrams. Okay, in NLM, it is very important to know the free body diagrams. So now we will see some types of diagrams. Okay, so the first one will be if a block is resting on a horizontal surface. So a normal reaction will go upwards and mg will go downwards. Okay, so if a block is placed on an inclined plane, okay, so okay, before that, let me tell you that normal reaction is always perpendicular to the contact. So this is our contact. So the normal reaction will always be perpendicular to the contact force. Okay, so and mg will be always downwards. So if this is theta, if we divide it in component, okay, so this will also be theta. This will be mg cos theta, and this will be mg sine theta. Okay, so now we will see another if, okay, in a pulley. Sir, wo thoda idhar. We'll see in a pulley now. Okay, so there's a block which is hanging on one side, and there's another block hanging on the next side. Okay, so this is M1 and this is M2. So M2G will act downwards and M1G will act this side downwards. Tension will be T1 and tension will be T1. It will be same. Okay, so another one we will see if two blocks are placed above each other. Okay, this is M and this is small m. Okay, so if we do like make a free body diagram of the small m, a normal reaction will go upwards and mg will go downwards. Okay, so if we make a free body diagram of the bigger block, okay, so it will be N1 up, which is giving normal reaction. It will be Mg, and the small m block will give a normal reaction on this block downwards. So it will be this block's normal reaction will be n plus mg, which this n is equals to mg. Okay, so now we will see the pulley trick. Okay, so in pulley trick, all the velocities will be in the same direction. Okay, so now there's a pulley. Okay, so this is V1, this is V2, but now here this is VC. Okay, so now VC will be the average of V1 and V2. So we calculate VC as V1 plus V2 upon 2. Okay, now we will see a moving pulley. Okay, so now a moving pulley. In this, now I will draw a big box. There's a pulley which is attached to it. Okay, so now if this string is pulled by V, then the block goes up with V. Okay, so second example will be there's a block. It's a big block, and there's again a pulley attached to it. There's a small block here, and if we move the big block with V, okay, so now this block will move in X direction with V and in Y direction in V. Okay, now we will see the combination of both of these. Okay, so there's a big block, again a pulley attached to it. There's a small block hanging on one side of the pulley, and if we pull this string with V and also this block with V. Okay, so first we'll consider this block. So if this block is moving, the small block will go here in V and in Y axis with V. Okay, now if we consider this, the string which is pulled with V, the block will again go with V. So this will go in Y axis, it will go with 2V, and in X axis it will go with V. Okay, okay, so we will now see frame of reference. Okay, so first we will see the inertial frame of reference. Okay, so in inertial frame of reference, it is when the observer is in non-accelerated frame. Okay, so and second one is non-inertial frame of reference. Okay, so this is when the observer is in the accelerated frame. Okay, so when this situation is there, we always use a term called pseudo force. Okay, so this pseudo force is applied in the opposite direction, in which the when in which the body is accelerating. So the pseudo force is applied in its opposite direction. This pseudo force is equal to the mass of the body into acceleration of frame. Okay, so now from these two, we come to know that non-inertial frame. Okay, so non-inertial frame plus pseudo force gives you inertial frame. Okay, and we can say that accelerated frame, okay, accelerated frame plus pseudo force gives us a non-accelerated frame. Okay, now, okay, so there's a man standing in this elevator. There's a block, there's an object, another object. This is observer B. Okay, and there's a man standing on the ground, which is observer A. Okay, so this block, particularly this block, will give a normal reaction upwards and mg downwards. Now, if this elevator is going up, it's accelerating upwards, then we will put a pseudo force opposite to it. That is, we will put it downwards, which is ma. This is the pseudo force which we are applying on it. Okay, so we will see another example. Okay, so there's an inclined plane. There's a man standing here. Okay, so there's a normal reaction up, acting upwards, and in this direction, it is this is mg sine theta. This will come as mg sine theta because this is mg, and this will be this will be mg sine theta, which is the pseudo force. So yes, so normal reaction will go upwards. If we divide it in the component, so this will be mg sine theta. Okay, this will be mg sine theta into cos theta. Okay, downwards it will be mg, and here when we divide it, it will come mg sine square theta. Okay, so now we will see constrained motion. So the constrained motion part 1. So now we will see constrained motion part 1. Okay, in this we have to know that if the pulley moves in x, okay, so the string will move in 2x. Okay, so we will see an example. Okay, so there are two pulleys hanging which are attached to another pulley here. There's a block here, and there's one more block hanging on this side, which is A. Okay, this string is not having any block attached to it. So this is block B. Okay, so if this block moves in acceleration in A, okay, so the strings will move in 2A. Okay, so when the pulley moves in A, the strings will move in 2A, and as a result, this block will go down in 2A. Okay, so now if the tension in the strings here is T, then the tension in the string here will be 2T. Okay, so another example we will see on inclined plane. Okay, there's a pulley here. It is hanging to another pulley here. There's a block attached to it, and there's another block attached to this pulley. Okay, so now when this pulley is moving in A, so the strings will move in 2A, right? So the block will move in this direction with 2A, because the pulley is moving in A and the strings will move in 2A. And even here, when the tension is T here and the tension is T here, the tension of this string will be 2T. Okay, now constant motion part 2. Okay, so in this we divide the resultant velocity in the direction of constant. Okay, so we'll see some examples. Okay, so okay, so this is point A and this is point B. Okay, so this is the theta. This is a stick or a rod which is placed between two sides of we can say a wall. Okay, so when this will move, okay, so when this will move, it will slide down in this direction, in this way. Okay, so the rod will go here in this, which we can call it B. Okay, so it is VB, and this side will move in VA. Okay, so now this is its radial velocity, and this will also be its radial velocity. Now, as this is the radial velocity, this will be the tangential velocity, and even this will be the tangential velocity to it. Okay, so another example of this is a pulley. Okay, so there's a pulley. Okay, its string is hanging down. There's a block. Okay, so now this string is in this attached to the block. Okay, so now when we pull this string in V, okay, so even this block will go in V, but this is this block will move here also in V. This will be its radial velocity. So now as this is V, this will all be its radial velocity, and this will be the tangential velocity to it. Okay, now another example of this will be, there's a rod here and there's a semicircular bowl, okay, below it. So this is theta here. Okay, so when this block moves in V, okay, so when this moves in V, this will be its radial velocity, and this will be its tangential velocity to it. So as a result, it will be like a radial velocity downwards and the tangential velocity upwards. Okay, another example for this will be on an inclined plane. Okay, so okay, now this is VA. Okay, this is point A, and this moves in VB. Okay, now if this is velocity B, okay, so we will look at this as okay, so this is moving in VB and this is moving in VA. Okay, so as it moves, this will go in this direction Okay, so this will be its radial velocity and this will be its tangential. Okay, and here this will be its VB tangential and this will be its VB radial. Okay, so now we will see Lamy's theorem. Okay, in this the an object is pulled in 3 directions. Okay, suppose this is the, okay, it's pulled in 3 different directions. So if this is F3, this is F2, and this is F1. Okay, this is angle A, this is angle B, and this is angle C. Okay, so Lamy's theorem always says as this was there. Okay, so F1 will be sine A, which will be equal to F2 upon sine B. Okay, so it's the opposite angle to the force. It's the opposite angle to it. So F3 will be sine C. Okay. Now we will also see an example for this. Okay, so if it is like this, there's a 4 kg block attached to it downwards. This string makes an angle of 60 degree with the upper wall. Okay, this is now tension 1 and this is tension 2. Okay, so when we make the free body diagram, okay, so it will be like, this will be T1 sine theta, this will be T1 cos theta, down there will be 40 Newton. Okay, so there will be a 40 Newton acting downwards and there's a tension 2 acting in the other direction. Okay, now we will see the problems of an elevator. Okay. Okay, there we will see the problems in an elevator. Okay, so now we know that we can see that while going up in an elevator, our reading increases. And while going down, we feel that our weight is decreasing. This is because of the weight we feel is the normal reaction exerted by Earth and not only because of our mass. Okay, so now we will see some examples. Now there's a person in an elevator. Okay, so okay, it's the elevator is accelerating upwards. Okay, so there's mg acting downwards and normal reaction acting upwards. So this will give us, okay, so the normal reaction of this will be equal to, okay, so when it's accelerating upwards, it is giving us this normal reaction, okay, m into g plus a. But now we will see when a person is decelerating, which is accelerating downwards. Okay, so the normal reaction will be up again. There will be mg acting downwards and this is the acceleration. So this will be mg minus a is equals to ma. So this will give us g minus a. So in both the cases, we can see that the normal reaction here when it is accelerating upwards is greater, which is whereas this when it is accelerating downwards, the normal reaction is less. Okay, so from this we can see that when we go up, we feel that our weight increases, and when we go down we feel that our weight is decreasing. Okay, so now we will see the applications of the second law in the second law of motion. Okay, so the first one will be block on a plane. Okay, block on a plane. Okay, so there's a block on a plane which is M. Okay, and it is pulled with a force in this direction. Okay, this will be theta. So this will, if when we divide it in components, we will see that it is F sine theta and this will be F cos theta. Okay, there's mg acting downwards and there is normal reaction acting upwards. Okay, so this is F sine theta. Okay, it's acting upwards. In this direction, it's F cos theta, and downwards mg is acting. Okay, so now we will see block on inclined plane. Okay, a block on inclined plane. Okay, so this is theta. Okay, so there's a tube kept here. The ball is going here. Okay, this is alpha. The angle is alpha here. So now, as we know, this will act mg. Okay, this will be mg sine theta, and this will be mg cos theta. Okay, so now as this is mg sine theta, okay, so this angle will be alpha. Okay, this is mg sine theta, this is g sine theta, this will be alpha, which will be g sine theta into cos theta. But then we have to remove the acceleration, which is this side. So acceleration will in this direction will be, when we will divide it in component, it will be g sine theta into sine alpha. Okay, in this direction, if we remove it, in this direction it will be g sine theta into cos alpha. Okay, now we will see block attached to string. Okay, when block is attached to a string. Okay, so but now we will in the first case we will see a massless string. Okay, so now, okay, in this there's a string here. Okay, so if we pull this side with a, like, it's an example of 10 Newton, and if we pull it by 10 Newton, the tension in this string will be 10 Newton. As these forces are equal, it is equally pulled by both the sides. But when a string is not pulled with equal forces on both the sides, um, we cannot measure the tension in the string unless and until some mass is attached to it. Okay, so now we will see a second example with mass. Okay, now this is a there's a block here. Okay, there's another block downwards. Now suppose this is 3 kgs and this is 2 kgs. Okay, there's a force acting with 100 Newton upwards. This is T. Okay, so now we will consider this as a system, and this will be and 50 Newton acting. So therefore, find the tension in point B. we will take the mass of this block, as well as, now if the mass of this whole rod is m, then at the midpoint it will be m by 2. So it will be m by 2 into g. Now when we find the tension in block C, okay, in point C, we will consider the whole mass of the rod plus the mass of the object. Okay, so it will be m plus m into g. Okay, now after this we will see the pulley system. Okay, now in the pulley system, when two blocks or two objects are hanging to the two sides of the pulley, the two strings of the pulley, so it's okay, so it's mg acting downwards, and this is going, okay. So when in this case we consider this whole as a system, and we take it upwards, like we, okay, so we take it like this. So this will be big mg, this will be small mg, this is small m, this will be the tension in them. Okay, now from this there are 2 points which we have to remember. In this, the acceleration will be m minus m into g upon m plus m. Okay, this is the acceleration, and even the tension in the string will be 2 big M into m g upon m plus m. Okay, so okay, so this is when we consider it as a system. Okay, so example 2 will be here now. On an inclined plane, there's a pulley here, a block here, a block here. Okay, suppose this is of 6 and this is of 3 kg. Okay, so this will go in 6g sine theta, and this will go down in 3g. Okay, so when we take it as a system, okay, when we take it as a system, we take it as 6 and 3 kg blocks. Now 3g is acting in this direction and 6g sine theta is acting in this direction. Okay, so now we will see the block attached to spring. Okay, now block attached to spring. A block attached to spring. Okay, now in this, now what is a string? Okay, a string is inextensible and also massless. Okay, a string transmits force and only it has a pulling force. Okay, now in this, what is a spring? Okay, now a spring is extensible and compressible, and also it is massless. Okay, now the spring transmits and stores force, but the spring is has both pulling and pushing force. Okay, now in this block attached to spring, okay, now spring constant varies. Okay, spring constant varies inversely with the length of the spring. So K is the spring constant. It is inversely proportional to the length. Okay. Now if we consider an example, now there's a spring here. Okay. Now it has length L and spring constant as K. When it is divided into 3:2. Okay. Now the length will be 3L. This length will be 3L upon 5. And this will be 2L upon 5. But as the spring constant is inversely proportional to the length, spring constant will be 5k upon 3 and 5k upon 2. Okay, now we will see the combination of springs. Okay, now when the springs, okay, are attached parallelly to an object, we remove the equivalent of it as k1 plus k2. This is k1 and this is k2. But when they are attached in a series, okay, this is k1 and k2, we remove its equivalent as, okay, 1 upon. So this is this is the thing we remove. Okay, now we will there's also Hooke's law. Okay, there's Hooke's law. Now a spring can even extend and also compress. Okay, so the spring force is Fs. This is delta x. Okay, now here we remove the Fs is the spring force. Okay, now delta x is the change of extend or compress when it extends or it compresses. Okay, and k is the spring constant. Okay, so Fs will be minus k into delta x. So when we have to calculate the compression or the extension in the spring, we use this formula. Okay, now the last topic is the cutting of spring. Okay, if now there's a spring here attached to one object and another. Now this is an equilibrium. Okay, the first case is an equilibrium, so this is of 2m. We can consider this is of m. Okay, so this will give this will give 2 mg downwards. Now as it is an equilibrium, even this will give 2 mg downwards. This will give mg and 2 mg, which is the tension in this string also. Now as a result, this will be 3 mg. Okay, now in the second case, we will consider that this string is cut. So therefore, tension in this string will be 0. It will this will go in 2 mg. Okay, so and it is that in spring, okay, it takes time to know what is happening downwards, so it does not compresses immediately after it does not compresses immediately when the string is cut. We are considering this when the string is immediately cut. So there will be a force of 3 mg only. This will not change immediately. Okay, the third case we will see that this is of 2m. Okay, now the third case we will see that the spring is cut, so therefore the tension in this will be 0. Now this will be like, now when this spring is cut, we will consider this as a system. Okay, so this will be 3m. Okay, 3 mg acting downwards. So this will obviously accelerate downwards. So the acceleration in this will be 3 mg upon 3m, which will be equal to g. Okay. Now we can consider another example. Okay. Now this will be 1 in this. Okay, now all the masses of this system, this object is m. Okay, now the first example will be in equilibrium. this will act in mg, as this is even, this will act in mg, this will go in mg, and the tension in the string will be mg. Okay, this will go in 2 mg, and this will come down in mg. So therefore this will again go up in 3 mg. Okay, so now in the second case, okay, in the second case, we will cut the spring one which is at the bottom. Okay, we will cut the spring. So here the tension will become 0. So now this will, as it is, go in mg. Okay, now here we will consider this as a system. Okay, so this will be as a system, and again this will go in 3 mg itself, because the spring does not come to know, because it is immediately after the cutting, so it does not come to know that the part is cut over here. Okay, in the next case now, okay, now in this we will cut the string. Okay, so the tension will become 0 over here. Now this will, okay, so this will go in mg, so there's no tension here, but this will not yet understand, so this will again go in 3 mg. Okay, so now we will see the fourth condition, which will be the last condition of the cutting of spring and string. In this case, we are cutting the spring which is at the top. Okay, so now here the tension will become 0. Now this is going with mg downwards. This is acting with mg here. This will go in mg, and the first mg will come. So this will go in 2 mg and go in mg. Okay, now this, as this spring is cut, we will take this as a system. Okay, now as we take this a system, then we will see that this will be of mass, this will be of mass 2m. Okay, so 3 mg is acting downwards of this mass. Okay, this 2 plus 1 mg will be 3 mg acting downwards. So therefore the acceleration will be downwards. So the acceleration in this will be 3 mg upon 2m, which is 3g upon 2. Okay, thank you. So there's a wooden stick kept here. So I kept, just with the holding of the stick, I just kept the phone here. So there are 2 tin vessels kept, and there's a wooden rod kept over it, and I just kept it like this above it, so that whatever I am writing can be visible.